A drop of water sits still at the top of a dam. It looks motionless, ordinary, almost meaningless. But in a few seconds, that drop will be pulled through a steel opening, enter a massive pipe, fall under the force of gravity, strike giant metal blades, and help tons of machinery spin inside a power plant. And the strangest part is this: it does not catch fire, it does not explode, it does not touch a single wire, and it does not vanish in the process. Even so, it can help create the energy that lights lamps, moves elevators, charges phones, and keeps an entire city running. Today on Invisible Structures, you will enter water's hidden path and understand how a river can become electricity inside a dam. To start, forget the idea that water turns into energy as if by magic. Water remains water. It enters on one side, passes through enormous machines, and exits on the other, returning to the river. So a simple question appears, one that explains the entire logic of a hydroelectric plant. If the water is not consumed, where does the energy come from? The answer begins before the turbine, before the generator, and before the high-voltage wires. It begins where the water is stored, elevated, waiting for a chance to fall. While it sits in the reservoir, it looks calm. But that calm is deceptive. Every liter up there carries an invisible force, stored by height. When a gate opens, the water does not need a motor to push it. Gravity itself does the work. It pulls the water downward, through a narrow, controlled path designed to turn a fall into pressure. It is like pinching the end of a hose. Water that once seemed calm suddenly gains speed, direction, and force. Inside the pipe, that drop is no longer alone. It travels with millions of others, forming a heavy, accelerated, concentrated column. At the end of this path, there is no light bulb waiting for the water. There is a turbine, and the turbine's job is to receive the force of the flow and turn the power of water into rotation. This is where many people are surprised. Water does not need to touch wires to generate electricity. It needs to spin a machine. The turbine turns a shaft. The shaft drives a generator. And inside that generator, motion meets magnetism. That is where mechanical force begins to become electric current. But the most important detail is still missing. Why does the water fall with so much force? Why can a dam do this better than a river flowing freely? And why can height matter more than the amount of water we see on the surface? To answer that, we need to look at the quietest part of the plant, the water resting up high. Because in a hydroelectric plant, the real secret does not begin in the roar of the turbines. It begins in the silence of the reservoir. The water resting high behind a dam seems to be doing nothing. It is not bubbling, it is not burning, it is not moving like a violent rapid. From a distance, it looks like nothing more than a vast, silent lake. But that is exactly where hydroelectric power starts to become fascinating. Because that water has something you cannot see with your eyes: height. And in a hydroelectric plant, height is energy waiting to be released. Think of a stone sitting on a table. While it is up there, still, nothing seems to happen. But if it falls, its weight gains speed and impact. The energy did not appear halfway through the fall. It was already stored in the stone's position. Water works in a similar way. When millions or billions of liters collect at a higher level, gravity gets an opportunity to pull it all downward with force. That is why a dam does not create energy from nothing. It creates a difference in height. And that difference is what turns apparently still water into mechanical power. This is where many people get it wrong. A free-flowing river may seem stronger than a calm reservoir. The current makes noise, crashes against rocks, drags branches, and foams on the surface. But to generate electricity on a large scale, it is not enough for water to move. That water must be controlled, its fall concentrated, and its drop turned into pressure. The greater the distance between the reservoir's surface and the point where the turbine is installed, the more energy is available in each liter that falls. This distance is called the head, and it explains why a hydroelectric plant built in the mountains can generate a lot of energy without a gigantic river, while a wide, deep, water-rich river that is almost flat may have a much lower limit. A large volume of water helps, of course, but volume without a drop is like having force scattered everywhere. A hydroelectric plant must gather that force into a specific path. That is why water does not simply pass through any opening. It enters controlled structures, crosses screens that hold back logs and debris, passes through gates, and continues through a pipe designed to withstand intense pressure. That pipe carries the water down to the lower section, where the energy of height has already become speed and force. Gravity makes the water accelerate, and the dam organizes that motion. It is not a random push, it is a guided fall. That is also why the water does not need to be consumed. It gives up part of the energy it carried by being up high. After turning the turbine, it keeps moving downstream. What changes is not the water's existence. What changes is its position. Before, it was elevated and full of potential energy. Afterward, it is lower, with part of that energy converted into machine motion and electricity. So when you look at a calm reservoir, you are not just seeing stored water. You are seeing stored gravity, a silent force waiting for a gate to open. And when that opening appears, the lake stops being scenery and starts working. In the next instant, that energy enters the powerhouse, meets the turbine, and turns an invisible drop into spinning metal. And if this explanation has already changed the way you see a dam, leave a like, because the most impressive part comes next. The exact place where the river becomes a machine. After gaining speed along its downward path, the water reaches the most impressive point in a hydroelectric plant, the powerhouse. This is where the river stops seeming like pure nature and begins to act like a precision machine. Before entering this industrial chamber, the water passes through the intake. This entrance is not just a hole in the dam. It is protected by enormous screens built to keep logs, branches, stones, and objects carried by the reservoir from entering the system and damaging equipment that costs millions. After those screens, gates control how much water will be released. Nothing happens by chance. The plant decides when, how much, and where the water will pass. Next, the flow enters the penstock, the giant pipe that carries water to the turbine. The name fits what happens inside. The water is confined, heavy, accelerated, and guided. It does not spread out like it would in an open river. It is concentrated in one direction, as if the entire force of the reservoir were aimed at a single target. That target is the turbine. A turbine works like an extreme water wheel, but instead of turning slowly in an old mill, it spins inside a closed structure, receiving pressurized water at carefully calculated angles to capture as much of the flow as possible. Each blade is designed to turn impact into rotation. The water strikes, pushes, curves around the blades, and makes the entire assembly spin with brutal force. But the turbine does not produce electricity by itself. What it produces first is motion. That motion passes into a shaft, a massive piece that connects the turbine to the generator. As the water turns the turbine turns the shaft, and the shaft turns components inside the generator. This is where the invisible transformation happens. Mechanical motion becomes electric current. The secret is magnetism. Inside the generator, metal parts rotate within magnetic fields. That motion makes electrons move through conductors, creating electricity. The water does not touch the wires. It does not enter the cables. It does not become liquid lightning. It simply delivers the force that makes a machine spin. The electricity is born afterward, inside the generator. And even when that energy appears, it still is not ready to travel to homes, factories, and distant cities. First, it passes through transformers. They raise the voltage of the electricity, allowing it to travel long distances through transmission lines with fewer losses. Then, near the places where it will be used, other transformers lower that voltage to safe levels. Now the hidden path of water begins to make sense. Reservoir, intake, screen, gate, penstock, turbine, shaft, generator, transformer, and power grid. Each piece depends on the one before it. Water does not leap straight into the wires. It first becomes force, then rotation, then high-voltage electricity. But notice the most important detail. All of this only works because the dam can control something enormous and dangerous. It holds back a massive body of water, releases only what is needed, and directs that force into the plant. Without that wall, the water would keep spreading through the river. With it, gravity gains a precise path. And that is where a question appears that almost no one asks when looking at a hydroelectric plant. Why does a dam have that shape? Why is the base so wide? Why are some dams curved? And why are there huge channels built to throw water away, even in a plant designed to use water? The next time you turn on a light, there may be a hidden waterfall behind that simple click. And if you want to keep seeing these structures almost no one notices, subscribe to Invisible Structures, because now the quietest part of the plant will reveal its own secret, the engineering of the wall that holds back the river. When someone looks at a dam, the first thing that impresses them is its size. But that wall does not have that shape just to look monumental. Every meter of concrete, every slope, and every curve exists because of one constant force: water pressure. And that pressure is not the same at every point. Near the surface, water pushes with less force, but the deeper you go, the greater the weight of the water above. It is like the bottom of a swimming pool. The deeper it gets, the greater the pressure. Now imagine that on a gigantic scale, with an entire reservoir pushing against the same wall for years without stopping. That is why many dams have a base much wider than the top. The lower section receives the strongest push, so it must be heavier, thicker, and more resistant. The top may look thin by comparison, but the base is where the structure truly faces the force of the lake. The shape of a dam is not decorative design. It is a direct response to the push of the water. In some places, the dam is also curved. That curve helps transfer part of the force to the sides of the valley or canyon. Instead of fighting the water alone, the wall uses the surrounding rock as an ally. It is a simple idea to understand, but a powerful one. The force trying to push the dam is spread out to the sides. But holding back water is not enough. A dam also needs to know how to release the excess. That is why spillways exist. They work like escape routes when the reservoir rises too much, especially during heavy rains. If the water crossed the limit without control, it could become a risk to the structure itself. So the spillway lets the excess leave through a path built for that purpose. It may seem strange to see a plant releasing water without sending it through the turbines, but that is safety. It is better to let water leave through a calculated route than to let it find an exit on its own. Another important detail is the position of the powerhouse. It is usually placed lower down, because that is where the water arrives after gaining enough speed and pressure to spin the turbines. The dam holds it high, the penstock guides its descent, and the plant uses the point where the force is concentrated. So that giant wall is not just a barrier in the river. It holds, directs, protects, and relieves pressure. Without this silent engineering, the turbine would not receive a steady flow. The generator would not have reliable rotation, and electricity would not arrive with the same consistency. Now comes the part that changes everything. Even with a huge dam, an impressive drop, and efficient turbines, two hydroelectric plants that look similar from the outside can produce very different amounts of energy. Why? If this structure feels clearer now, hit the hype button. It helps invisible structures enormously. And the next detail shows that inside a power plant, not all water is worth the same. Even after understanding the drop, the turbine, and the shape of the dam, one detail still changes everything. Not all water generates the same energy. Two hydroelectric plants may look similar from the outside, but produce very different amounts. The explanation comes down to three factors: the height of the drop, the volume of water, and control over the right moment to release that flow. A very tall dam with little available water has a limit. A huge river with little elevation change has a limit too. For the plant to generate well, it needs to combine quantity and height. It is the mix of mass and fall that determines how much force reaches the turbine. That is why the reservoir level matters so much. During dry periods, the lake drops, and when the water is lower, part of the energy stored by height drops with it. The plant can still operate, but the available force is no longer the same. The reservoir is not just a supply of water. It is a supply of position, of gravity, of a fall waiting to happen. That is also why the release of water must be controlled. During peak demand, when millions of people turn on lights, machines, showers, trains, elevators, and equipment at the same time, the grid needs more energy. In some cases, the plant can increase the flow of water to respond to that demand. It is not just opening and closing a giant faucet. It is balancing the river, the reservoir, the turbines, and the electrical needs of entire cities. And there is an even more curious version of this idea: pumped storage plants. They do something that seems absurd at first. At certain times, they use electricity to pump water back uphill. But there is logic behind it. When there is excess energy on the grid, that energy can be used to move water to a higher reservoir. Then, when demand rises, the water flows down again, turns the turbines, and generates electricity. It is as if the mountain became a giant battery. Instead of storing energy in chemicals, it stores energy in height. A hydroelectric plant is not just a dam, a turbine, or a powerhouse. It is a way of organizing gravity. When the water is high, the energy is waiting. When it descends, the river stops being scenery and becomes electricity. And the next time you look at a dam, you may not see only concrete holding back water. You may see an invisible structure storing force in silence. If this video changed the way you see a hydroelectric plant, subscribe to Invisible Structures and tell us in the comments, what surprises you most about turning gravity into electricity?